So, so in the last video we talked about how you can determine the the stiffness matrix and the force. You can relate the force at each of the nodes within a matrix and the stiffness of that element with the displacements of the nodes of the element. So in this video, we're going to talk about how you can create your three global matrices that will define the entire system. Or basically, will define all the elements within their system. So, in this example, we have two elements, element 1 and element 2, and we have three nodes. We have node 1, node 2, and node 3. So note that node 1 is only part of element 1, node 2 is shared by element 1 and element 2, and element 3 and node 3 is only within element 2. Alright? So we're going to define each element using the following equation. So if we go back to the last page of our document, we had given this equation here defined was our equation for our bar element. All right. So we're going to define the value of our bar element for both element 1 and for element 2. So all we're doing is writing this equation for each of our individual elements. Okay. So for element 1, okay, we have our two nodal forces that are applied at 1 and 2. So what we'll have here is we'll have Fx1 and Fx2. Okay, so that's our nodal force that's applied at 1 and our nodal force that's applied at 2. Okay, and that's going to be equal to our stiffness matrix, which is just going to be equal to, which we'll just denote as K1, negative K1 on the first row, and then negative K1 and positive K1 on the second row. And then our column on the right-hand side will be our displacement. So this would be the displacement of our two nodes. So the leftmost node is node 1, so we'll use a U1 to denote that node, and then displacement of node 2 will denote with U2 for being the second element in our column vector. Okay, so remember that we can calculate K1 is just a constant that's equal to the area of element 1 times the elastic modulus of element 1 divided by the length of element 1. Okay? So, we can do the same process for element 2. This would be a great time for you to stop the video and try this on your own before I go through it to see if you get the concept from element 1. So for whatchamacallit, for element 2, which is shown on the right hand side here, we have our two nodes, 2 and 3. So we have Fx. So we're going to have a force at Fx2, and we have a force at Fx3. Alright, so those are our nodal forces, and those are going to be equal to our stiffness matrix for element 2, which will just be equal to negative K2, negative K2 on our first row, and minus K2 and positive K2 on our second row, times U2 and U3, where U2 is the displacement of node 2 and U3 is the displacement of node 3. So what we can do is what we essentially have here is we have three algebraic equations. We have an algebraic equation for Fx1, we have an algebraic equation for Fx2, and we have an algebraic equation for Fx3. Now, we technically have two equations for Fx1, Fx2. So what we can kind of think of it as we have two equations. I'll call them 2a plus 2b that we're going to add together. Okay. So what we can do is we can combine our matrices together for element 1 and element 2, combine them into a single matrix where we have our first stiffness matrix. I'll highlight in red here. All right. So this is for element 1, and then for our second stiffness matrix, I'll highlight in blue. All right, and this is from element 2. Okay. So what you'll notice is that if we add our nodal forces will be on the left-hand side of our matrix, and then the shared nodes, our nodal forces will be added together. Okay, so if we take our nodal forces and we add them together, what we end up getting is our externally applied forces at each node, and that will be equal to our global stiffness matrix, which we'll call K global. All right, and our times our displacement matrix for all of our nodes. Okay, so we call this our global displacement matrix. Okay, so if we so what we end up getting is we end up getting our equation for our system, the global system, or the entire elastic body to be the externally applied forces need to be equal to the global stiffness matrix times the global displacement matrix. So for bar elements, you can remember that all the element matrices will join at the diagonal. So for example, we had K1 plus K2, right? And then the net forces applied at our nodes is our global forces, our externally applied forces. So in this case, we have F1 would be equal to our reaction force. All right, and that's unknown. We don't know what that value of that force is. F2, there's no, if we go back to our original problem, there was no externally applied force at F2, so we can set F2 equal to 0. And then we have our external force, F3, all right, which is a known force that was given to us. Okay, so in short, we can define our stiffness is for our stiffness matrices for each of our individual elements, and then we can combine them to create our global matrices for our global externally applied forces, our global stiffness matrix, and our global displacement matrix for all the nodes in our system.